case, this is in Z join 1 over P and independent of L. Okay, so that's the kind of motivating theorem. So let me make some remarks. So the first remark is if the characteristic is 0, then this is standard because you can compare with singular cohomology and Q coefficients, and so then it's clear. And also by sort of a spreading out argument, the key case is K is FQ bar, which for the most of the remainder of the talk will be my assumption. I mean, this is a geometric statement, but it becomes important later to work over FQ. And I mean, many cases are known. So for example, if X is proper and smooth, then this is the Lefschetz trace formula. And so a number of cases. Let me just mention sort of one case. If F is proper, then the analogous statement for F upper star on R gamma C compactly supported cohomology is known. Well, instead of Z adjoin 1 over P, I think you have to just put Q. Replace Z join 1 over P by Q. This is by Fujiwara's theorem. So this talk is really about the cases that are sort of messy when X is singular, open, things where you can't use duality, for example, to approach it. Okay, so what's sort of how might you do this sort of based on SGA 5? Well, I don't think you get it quite this. You still don't get it for X smooth because there's two things. If F is proper, there are two things you can do on compactly supported cohomology, and if X is not smooth, well, in general, they're not the same. And so this is for F upper star. There's also an F lower star, which is not known, I believe. Yeah. So how might you sort of how to get started? How to start? Well, so you compactify. So I'll draw it this way. Here's F. And I put the identity map here. So you might just choose a compactification, X into X bar. That will at least get us proper. So let me put that here. And now, of course, you might try to extend the map. It may not extend, but you can blow up in the boundary to extend the map. And so you get some C in here, some diagram like this, C1, C2. Let me call this J prime. And so what do I want here? So I choose my X bar to be proper over K. And so the C1, so C and will also be some compactification. And because of the way I set it up, X will still be C2 inverse of X, so this X here inside there. Okay, and then you consider the complex K, which I'll write as J lower star QL, and sort of following standard conventions, this means rj lower star ql, but I'll almost always omit the r. You get an action of this. So this is a correspondence. You get an action on this complex, which I'll write u c1 upper star k, c2 upper 3k. And I don't want to emphasize too much sort of these technicalities, but the main point is that even if you start with this kind of question, you very quickly end up in the setting of a correspondence acting on a complex. And sort of this is the right way to do that. And then you can try to apply SJ5. And so you have the Lefschetz trace formula. Developed in SJ5, which says that, well, in this setup, the trace of f upper star acting on r gamma xql, which just by the way I set it up, is the same as the cohomology over x bar with coefficients in that complex k, is going to be a sum over certain and I'll explain what the notation is here. But you have a sum over certain sort of components of the fixed point locus and certain local terms z, k, u. Okay? And so I'll explain what this means, but I just want to get the formula sort of on the board. And so if you're interested in independence of L properties of this thing, you sort of end up studying these local terms and trying to prove independence of L properties of these local terms. Okay? So let me sort of now go to the setup. So the general setup I'll consider is the following. So I'll work over, I apologize for the change of k, but I want a ground field k, which will be fq usually, and then embed it into some algebraic closure, because now I want some Frobenius action. I mean, in this setup, if you start over fq bar, this is a finite type, and so you can choose an fq sitting inside there where everything is defined. Then I'll consider correspondences. Correspondences, which is just a map like this of, say, separated finite type schemes. And for such a correspondence, you have fixed points, which is the fiber product of this diagram. This notation. So you take the fiber product with the diagonal. Can you see this board? It's OK? Yeah, OK. So then you have a notion of an action on a complex. So if I have some object, so an action is just a map like this in the derived category. So what are these local terms? Well, the definition in SGA 5 is quite complicated. And I should also point out that in SGA 5, there's some assumption of properness on this map. So that was removed by Warshawski. And you can define them sort of more generally. And that's a simpler definition. But anyway, so there's a map which goes from sort of the space of actions to this cohomology group where this is the dualizing complex. So I'll write it like this. U goes to square brackets U. And then this for Z, a proper connected component of this fixed point locus, this local term at z of ku is defined to be the proper push forward of this class. So it's usually written integral of this class square bracket u. Okay. So I write these formulas up because I think it's important to recognize why this should sort of be independent of L and why you sort of maybe should work at this level already. So this is what people call Borel-Moore homology, which is sort of the natural target for cycles. So in sort of once you sort of think about this, maybe you want to take one step back and try to realize this class as the class of an algebraic cycle. Okay, so that's sort of, I think, a better.
In this sort of big-time generality, you have this issue of the sense in which the K, which is this L-anic,
yes,
is independent of L.
Yeah, so this will be sort of the central theme of the talk. But let me just point out that it's a very good remark. I mean, you can do something kind of stupid, which is just, if you have something here where you get independent of L, just multiply it by an L-adic number that's not a rational number, and then you know. So how do you choose the u? That's somehow one of the key themes. So I'll come back to this. That's somehow. But before I do that, let me just sort of mention that sort of an example where everything goes great is if C and X are smooth of the same dimension. And then the C2 upper street QL is just QL canonically. And so there's sort of a natural map staring at you, namely the identity map. You have to worry a little bit about this identification. But so there's a canonical U from C1 upper star QL to C2 upper streak of QL. Of course, the fixed point locus may still be singular, so this might be sort of a non-trivial gadget, but it's still true that U, in this case, this class U is the class of the cycle which is obtained by C upper streak of the fundamental class of the diagonal. So here you have this Cartesian diagram. Because this is a local complete intersection morphism, you can define, and actually this is two, so you can do sort of refined intersection product in the style of Fulton. So this is, I don't know where the accent goes on a Fulton. Sorry. But you, oh, I had it correct. OK, I should just follow my instincts. Yeah, so you can do this sort of intersection theory, C upper streak, to get a cycle on the fixed point locus, and then you can take its cycle class, and that is, in fact, what this square bracket U is. Okay, and so that is sort of independence of L in the best possible way, because, I mean, it means also that the problem of calculating this thing is, it's an intersection theory problem, which may or may not be difficult. But OK, so I think this is due to Grothendieck. So this yeah. All right. So that's would be the ideal. So it's unfortunately doesn't go quite so nice, but let me state sort of the main result. So so if you want to sort of now go for complexes, the sort of first place to start is to think about Lie sheaves. So let me discuss that. Okay, so let me still work in sort of C as before, and let me assume that C and X are still smooth of the same dimension. means the general results are reduced to sort of these kind of cases by alterations and so on. So, okay, and maybe same dimension. Let me give it a name, D. Okay, and let's say we have V is a lease QL bar sheaf on X. Okay, and well, so in this case, because everything is smooth of the same dimension, I'm looking at a lease sheaf. C2 upper streak V is just C2 upper star V. Okay, and so in this case, what I'm asking for, so an action U is just the same as a map. So I'll think of it as a map like this, C1 upper star V to C2 upper star V. Somehow that's a little more pleasant. And what you can do now is just restrict this map to the fixed point locus. And so you can think about U sort of on the fixed point locus. That's just an endomorphism, V restricted to the fixed point locus to itself. And you can just take its trace, right? So this gives, I'll write it this way, TZU defined to be just the trace of U restricted to Z, which is an L-adic number. This is H0 Z QL bar. Okay, so this is not the local term, but the difference is somehow understandable in this case. So let me put that as a little lemma. If Z is proper over K, then you can think about this local term Z BU, and you can also think about this map here, and you can look at sort of the local term that sort of gives the intersection part. Okay, so there's sort of a canonical action, which is the one I described. So if you have to work through the formula, but I like this number better because it's more functorial. So the local term, sort of, as you can see from just sort of this description with intersection products, is not going to be very functorial as I start modifying X. But this number here has sort of simpler definition, so we can work with that. OK, so that's the number. So I'll study this thing here. OK. All right, so let me talk about the question of how to choose the U. Yeah, so let me take K to be my finite field, and let me now assume that my V has sort of the best possible properties. So I'll assume it's pure weight 0, geometrically irreducible, and I'll assume that it has connected monodromy group. The general story, this will be sort of after a rather elaborate devisage. You can sort of think about this case. And what this implies, oh, and let me assume that the C1 and C2 are dominant. Still smooth of the same dimension, but I didn't put that before. So this implies that the determinant is trivial, is non-canonically QL bar, and also that I want my C1 upper star V and C2 upper star V to be irreducible. So it's generically finite, homomorphism. And that sort of these assumptions imply that there exists. So because these are irreducible, it's it's either a yes or no question. Are they isomorphic or not? And so, so there, well, I guess that's always a yes or no question. But the point is that if they are isomorphic, you can choose an isomorphism. And sort of the good normalization is with the determinant of u being 1. Okay? And this makes sense even though this isomorphism is not canonical. Okay? And if you think about it, for some reason, this took me a long time to realize, but if you sort of think about motives and imagine these as being motivic, this kind of condition is the kind, it's a linear algebra condition, and so that sort of should be this sort of right map in the category of motives, if you imagine these as being some kind of coming from a Q linear category. So that should be the good choice. But it's unique up to mu r. And up to mu r, where this is the rank. Was that your comment? Yeah. Okay.
But I'm still, I mean, what about this, so to speak, independence of element of B?
Yes, I'm coming to this. Yeah. Yeah, but this is, let me do it one step at a time. Yeah. Okay, so, all right. So this is a real nuisance, actually. But I'll say a few words, but mostly sweep it under the rug. But so theorem 2, I'll just say theorem. With these choices, or this choice of u and assumptions, for every z, we have T, Z, U is an algebraic number. Okay? So that's sort of the first theorem. And now let me come to your question. So now we have to worry about the partners. Okay? So okay, so now let me fix an isomorphism QL bar to C, and let's say L prime is a second prime, is another prime, and L can be allowed to be L prime. So I think that's something I learned from your book. I mean, one thing that one should worry a little bit about is I'm working, everything is here over Q bar. And at some point, you want to go back down. And it's very convenient to then think about sort of when you take the same prime in two different embeddings. And that's sort of a well-known trick, I guess. So, but anyway, so here Drinfeld tells us, so my x is smooth here, that there exists a least QL prime bar sheaf V prime such that V and V prime are, I'll say, Frobenius compatible, meaning that if I look at a closed point and look at the characteristic polynomial for Frobenius, then those are the same. I guess I need an iota prime here. Under these identifications. Okay. In the case of curves, this is due to Laforgue, and then Drinfeld has this fantastic argument to give in this case. Okay. And many properties carry over that you can sort of read off using linear algebra. So, for example, if the weights match up, and I mean this is in the finite order determinant case, and so on. So I can apply the preceding discussion also to V prime. Okay, and let me state the theorem. So again, there exists a U prime from C1 upper star V prime to C2 upper star V prime. determinant of u prime equal to 1 such that ℓz of u is equal to ℓz of u prime. Okay? Now, my z here, let me now get to this sort of thorny issue of the root of unity. So here I have some component here, and the way I'm stating it is for a fixed z, there is a choice of u prime so that they match up, right? And you might be off by a root of unity a priori for some other thing. And unfortunately, I haven't been able to prove that you can choose the same u and u prime for all z, but I can do it after extending the ground field a little bit. Okay, so sort of if you look at my paper, there's some technical stuff about sort of replacing fq by a slightly bigger field, in which case you can. So I would rather not state the sort of technical part, but it's a real issue. Okay. All right, so that's sort of the story for sort of irreducible sheaves. And even in the case of curves, I think, so I had for a long time hoped that if you're in the case of a curve, this should sort of somehow come out of the Langlands program. As far as I can tell, that's not true. You can do some special cases like a finite order automorphism of a curve or something like this. But in general, unfortunately, that's not, doesn't seem to be available, or at least I would love if someone could tell me how to do that. So I use a different argument. All right, so let me give sort of a variant statement, which I think is interesting in its own right, and it's also somehow key in the proofs. So let me consider y a normal surface. Again, this could be more general, but let's say over k. Well, it's over a finite field. And let's suppose I have a smooth pointed curve. Not proper, but just say an affine curve. And let me suppose I have two maps from this curve to my y, my surface, and f of z is equal to g of z is equal to some point x. So they have sort of a common point. And let me also give myself a v, which is geometrically irreducible, pure, weight 0. And let's see, what I also want v upper star, f upper star v isomorphic to g upper star v, and these are irreducible. It's a rather special situation, but the point being that this is something about surfaces. These are irreducible on sigma. Okay, so let me draw a picture. So here's my surface y. And then I have my curve, sigma, and my point, z, and my two maps here. And they do something here, but maybe it's complicated, but they have some common point in the image. Okay? So then you can ask about sort of independence of L in this context also. Let me raise this up. All right, so let me state a theorem. There are a few assumptions that I would prefer not to say now, but so notation as above, plus a few technical conditions. But I think it won't help if I sort of start writing them out. So then there exists a U from F upper star V, G upper star V, with trivial determinant such that, well, you see now the dimensions are all off, so I really don't want to work with G upper shriek. You could think of this as a correspondence, but somehow the dimensions are not good. So it's better not. It's better to think of just sort of these sort of local traces. So I'm just going to take the trace of the stalk. Let's see. And I'll put this in Q bar. So it's like this, and independent of L in the sense over here. Now you have to be a little careful because Drinfeld's theorem is in the smooth case, and here I'm in the normal case. So I'm assuming that I have my V prime for this independence of L statement. But OK. So why is this sort of a good thing? So let me make sort of, this implies sort of the earlier results. And so the idea is the following. If you have your correspondence here with the C and X smooth, and the map's dominant, like in Lafort, you can choose some curve mapping in, which is surgex onto the fundamental group. So take y in the fixed point locus of C. And then you can choose sort of pointed curve, sigma z, let me call that map A to C, such that I can write it like this. Map of pointed schemes, such that sort of A lower star on the map on fundamental groups is surjective. And then out of this, let me draw another picture. You can so do the following. So I'll write sort of sigma wedge sigma, which is just take two copies of your curve and glue them together at your point. So let me call that Z there. And then that maps to X by sort of C1A wedge C2A. And then you can start thinking about deforming this. And here it's important that you don't do a proper curve, but do some kind of open curve. And you can sort of find a diagram like this, where this is a normal surface. Okay, and so then sort of the initial question about calculating this sort of local trace at this point becomes one of sort of pulling back here and then going back. And so somehow this question lets you get some control over the geometry, because at least now you're down to a surface as opposed to some general scheme. All right. Let's see. So maybe I'll discuss a bit the case of, so now, I mean, maybe I don't want to say any more about the surface case. Let me say a sort of bit about how do you go beyond irreducible Lie sheaves and to more general Lie sheaves, and then I'll say something about sort of the general story. But let me talk about push forwards along open immersions, which is the key case in many ways. I apologize for the notation, but let me set it up. So we have this over FQ, smooth of the same dimension again, the C1 and C2 dominant. And let me now think about an open embedding U into X, dense open. And I'll assume it's invariant. C1 inverse of U, C2 inverse of U, and that the complement D, X minus U, is a divisor with normal crossings. Okay, so the kind of situation you could end up in using de Jong. So I guess the one thing about de Jong is now you have to work with sort of quotients of quasi-projective schemes by finite group action. So there's some issue with integrality statements, but OK. And then I have my L and then an iota, and L prime, iota prime. I'll have a K and a K prime. These will be Lie sheaves on U, which are Frobenius compatible. And then for every n bigger than or equal to 0, I'll also consider the twists. Twists, sort of natural way to twist the correspondence by a power of Frobenius. So, and there's an action. U prime. OK, so there, I don't want to write the formula. What assumptions? So the goal then is to, so I want to prove independence of L. I didn't say the U's. Sorry. I also have actions here, which I'll write U and U prime. So I want independence of L for the push forwards of these actions. Independence of L for these J lower star of maybe the twist by Frobenius. So U prime twisted by N, which act on so J lower star K and J lower star K prime. Okay. So, well, of course, I need some assumptions because I have just chosen my U and U prime arbitrarily. So let me say sort of some assumptions. So let me assume K and K prime have trivial determinant connected geometric monodromy groups. So again, sort of not a too serious a condition. And second is a condition maybe I won't spell out in detail, but I need some kind of unipotent local monodromy. At infinity. So you have some suitable compactification where there's some, the monodromy along the boundary is unipotent. And then third, and that's somehow the most serious, is that you have some dense open V inside U where such that the CIs are quasi-finite over V, and for every fixed point after possibly twisting in V, the characteristic polynomials of, then you get sort of these endomorphisms, UZ twisted by N, U prime twisted by N, are equal. And here equal means that they're in Q bar adjoint T and equal under these identifications. Okay, so in other words, you have some Lie sheaves and you have some open, and maybe you shrink even further to the open, but there you know that when you look at the characteristic polynomials at fixed points, they're equal. So they're somehow compatible on some open. So then theorem in this setting is that for every Z, if you now look at the whole so pi naught, every component after possibly twisting, the local terms are in Q bar and equal of the push forwards. That's sort of what you would expect, of course, but you might worry a little bit about this condition because maybe you shrink and there are very few fixed points. In fact, that's not true. You always have lots and lots of fixed points. In fact, you have sort of a dense set of fixed points. You have some kind of Chebotarev density theorem in this context, which is due to Warshawski. So let me say that. Write it. So remarks. So one, Warshawski implies that you have sort of as many, sort of dense set of fixed points even after shrinking over V. Okay, so I mean you have to make sense of what density here means, so maybe I'll draw a picture, which I like, which I hope maybe clarifies. So let's suppose C is here. Here's X. And here's sort of my other copy of X, C, X, X. And so if I have sort of two fixed points, Z and Z prime, mapping to some X and X prime, if you think about sort of the topological situation, there's something very naive you can do. So we have these maps here. You can just choose a path between, say, Z and Z prime. And then if you look at the two projections, sort of you get one path here, and maybe you get another path here. And so you can look at their difference. So a correspondence sort of gives you classes in pi 1. And this density statement says that you get sort of a dense collection of elements by these procedures. Okay, so that when you sort of just look at the paths, fix one fixed point, and look at all sort of other fixed points you get even after twisting, then you get actually lots of elements of pi 1. Yeah. Yes? No. So I have to, you mean in condition assumption 3? No, I have to assume that for all n, maybe after some n naught, the characteristic polynomials agree over the open, right? Because I might have no, for fixed n, I might have nothing. Right? It's I think I need for all n, yeah. Because I mean, the argument here, first of all, I want to reduce down to k and k prime being irreducible, right? And so already there, some density result is needed to make sure that if they sort of all the different factors, the sum of the different factors agree, then the individual factors agree. Yeah. Right. Okay, so that's the first remark. Let's see. So the second remark, it's, I think maybe it's an idea I sort of like. Well, anyway, so so what is the sort of one key idea? So if you're looking at this j lower star k, or maybe first reduced to the case k is irreducible. So you can think of this as I mean, it's a complex, but you can sort of do a little bit better, and this is where the unipotent local monodromy condition comes in, which is to think of this view, this as a module over sort of j lower star of QL. And what do I mean by that? I mean, here, if I was just working topologically, I would view this as a differential graded algebra. I have to be a little careful here, because to do this, you have to first, at least I do it in sort of a naive way, reduce to torsion coefficients. And then it's not a good idea to view this as a sort of differential graded algebra. But actually, there's two things you can do, at least two things. You can either sort of relax associativity, which is work up to homotopy, or you can actually, sorry? Well, so I mean, if you want to view this as a commutative differential graded algebra, I think you can do it using classical methods, maybe using Johan Peters stuff, that's possible.
Sorry, I was wondering what you meant by relaxing associativity.
Oh, okay, no, so I mean, you can do sort of an what do you call it, an infinity algebra kind of thing. Or you can do it sort of, and which is what I do, a more naive thing, which is forget commutativity. So for torsion coefficients, you can still do sort of non-commutative differential graded algebras, and that works just fine. So that's just sort of something. And in fact, I should say that this involves, so this uses something called the flat model category structure, which is also used by this seems to have come up in other contexts, so let me sort of mention in particular Zheng and Liu's work on sort of the base change theorem for F lower Schriek in the sort of higher category context. So this seems to be a useful tool. So yeah, and let me just make some other remark. Which is in the case when x and c, well, let's say x equal to c, and c is given by a finite order automorphism. In this case, you can do this directly using Laforgue. So in this case, Laforgue implies that the local terms are given by algebraic cycles. Okay, which actually enters into the proof in some key ways. All right. All right, so let me finish by saying a few words about sort of what kind of general sort of what statements can you expect for a general K. So just an object in the derived category. So I'm you know, the problem of choosing the U is replaced by some assumption that you already have it over some open. So that's sort of in the general case. There's another thing you can do, which is if C2 is quasi-finite, then you have so-called naive local terms. So let's suppose we have a fixed point mapping to some x. And if I have a k in here, and then some map C1 upper star k to C2 upper street k, then it induces just an endomorphism of the complex kx to kx, and I can consider the trace. Okay. Now, I think the traces aren't quite enough. You also have to sort of compose the correspondence to sort of think about characteristic polynomials. So you need to take sort of powers. So that's the general. You can also consider sort of a CM, which is the M-fold composition. So if it's just an endomorphism, then it's just the nth power of the map. And sort of the composition of the UM and now let me again give my L and L prime up here, but now K and L iota, L prime, iota prime as before, except let me take K and K prime to be just complexes and not these sheaves or anything. And now the assumption here is, so let's assume, so this is sort of that the so-called naive local terms are compatible. So for every n m bigger than or equal to 0 and z in the fixed point locus of the m-fold composition and then maybe twisted by Frobenius sometimes, that the trace of these acting on kx. So this is just an endomorphism of a complex, so I can take its trace. Prime. Let me suppose that these are in Q bar and equal. Okay. So this stuff about composition is a substitute for not saying characteristic polynomial, because I now have complexes. So this seems a convenient way to just encode that. And then the theorem, which I'll say weakly compatible implies strongly compatible, is that if I now look at the true local terms, so I have some n and m and a proper component of the fixed point locus, we have the local term z k u m twisted by n is equal to the local term z k prime u m prime twisted by n in Q bar. Okay, so, and here you could probably say start m. You should start from, I guess m should be actually bigger than 1. Let me do it this way. And you could probably consider just an n sufficiently big. So this implies, for example, remark, this implies, for example, things like stability under duality of sort of this condition of having naive local terms equal of condition that naive local terms because, well, there's some, by what the terminology, I suppose you can guess that strongly compatible implies weakly compatible. So, once you have this, the true local terms behave well with respect to duality, and so you get this kind of statement. So Gaber, this is for Frobenius compatibility. Yes. No, let's see. I'm trying to think if I use Gaber anywhere. Yes, I do, I think, because the argument for this kind of thing, I mean, throughout I'm assuming that my sort of complexes are Frobenius compatible. So if I want to make some arguments about the duals, I think I first need to know. I'm not sure, but I suspect that Gaber is used. Well, Gaber is used in many places, but yeah, certainly it probably is in there too. Yeah. Okay, maybe I'll stop there.